this ED441, now I'm using a Mac M1, so for me, getting a 64-bit ARM machine is very easy. You just install Linux and you're on 64-bit ARM. If you have an Intel processor machine, like a Windows machine, then you'd have to do ED40 first, where you download an Ubuntu machine I prepared that emulates an ARM processor. But in our case, the default install of Linux is going to be using an ARM processor, and I can verify that with uname -a. And that shows you I got ARM64 and I'm running Debian. All right, which is very close to Ubuntu, but not exactly the same. So let me just make this big and move the instructions over. All right, so we've made a vulnerable program here. All right. So here's the vulnerable program. So it's got some libraries and some global variables. But the point is, reads a password, and then it prints some addresses telling you where things are being stored. It runs hex to raw, takes raw hex input, so I can put in null bytes. I'm not taking characters that are interpreted because when I do ARM exploits, I haven't found any way to do it without including null bytes. So I had to write a program to make it easier to do that. Then it's going to run this test PW. That's going to just print out some stack values and return, and then you're all done. And we're going to exploit this program. Up here is just code that turns hex into integers. So it's nothing special. All right, but the point is, I take the input from the command line argument, I read the input. I read the input here. All right, where did I read the input? I'm losing my, here I read the input. Okay, here I entered the password. Okay, and I read it up to 2,000 characters and put it in this variable called hex, which is a global variable. So you can get up to 2,000 characters in. Now every 2 of those characters are going to turn into a hex value, which is 8 bits, which will turn into 1 printable character. But anyway, here I'm going to copy it into a password that only has room for 10. So that's the buffer overflow. I might have 1,000 characters, and I'm going to copy it into something only with room to 10. So we should find buffer overflows in here. So I compile this thing. If I run file on it to see what I've got ARM 64-bit code, which is what I want. So I can run this thing and give it a password, and let's make it bigger yet. All right. And if I give it Control C and move my window so it's not vanishing off the bottom of the screen, there we go. So if I run this thing, give it a password like AA, it takes it. Now, by the way, notice if I give it AAA, it's going to complain because I have to give it 2 characters for every byte. I'm putting it in hex. So it's not going to accept anything that's an uneven amount of characters. But AA works. Now, notice I'm getting the same value for the password address every time. That's because I turned off address space layout randomization. Remember, you often have to do that for these projects, and here's how you do it. You have to escalate to root and then put 0 in this system variable, proc sys kernel randomized VA space. I've already done that on this machine, but if you're seeing different values all the time for the addresses, then you have to do that before proceeding, or you won't be able to finish this project, because we're not doing fancy things. We're just doing the old-fashioned buffer overflow where you put in a fixed address, and you have to be able to figure out where that address is. All right, so now if I run this program, and I give it, say, 10, 10, 10, 10, it takes that. Now I'm just going to give it something longer. Here it is. Some 10s, then some 14s, 18, 1Cs, and so on. Now it has a segmentation fault. So this is the observation of the buffer overflow. Some of this code ended up in some system register like EIP or EBP and caused it to crash. So we observe it in a debugger, as usual, and run it, and feed in that long thing. And here it is, and it prints the program counter here, and if you don't believe that, you can just do $PC to see the program counter. And as you can see, it's trying to go to this address, 24, a bunch of 28s, and then some 2Cs. So this part of the input ended up in the instruction pointer. So this means I can totally control the box. I can move that code to any address I want. So that's good. All right. And now, if I do disassemble main, see what's going on here. then I can see that here's where it calls test PW, which is where the overflow is. And when it's done, it should return to this address, which is a bunch of A's and then C40. So I can just remember that. It looks a bunch of A's and then C40 is the expected return address. So now we can examine and see where that is on the stack. So if I list some code, I found out 39 to 52 is a good region of code. Here's where the overflow is at this mem copy. So I'm going to put a break on line 46. So I'll see the condition of the memory before it tries to return from that program, from that subroutine. And so now I run it, run, and say, yes, I want to start it over. And then I put in a short thing, 10, 10, 10, 10. And now it has the breakpoint. So now I examine the stack. All right, and so you see the 10, 10, 10, 10 is here. That's fine, but remember, the OC40, it's here. And by the way, this is what a 64-bit address looks like when you examine it with X. It shows you 32-bit words. So this is the high value and this is the low value. If you don't want to see it that way, you could do 6G here to see giant words. And now you'll see that address intact. You're seeing now 8 bytes at a time, 64 bits. Anyway, this is the return address, and this is why people say you can't exploit buffer overflows on ARM, not so easily, because the return pointer comes before the local variables. So if I make this longer, I'm going to overflow stuff down here, but I'm not going to hit that return pointer. But that's why I made the overflow in a subroutine, not in main, because it turns out this value down here is the return pointer used to return to the operating system when the program ends. So there is a return value I can hit. It's not the return value for this function, it's the return value from main. But I can still hit it, so that's why we're getting the results here. All right. So if I do next command, and next again, and next again, if I can only hit the right one, there we are, then I get a crash, and you can see this is off to the operating system. All right. So, not terribly easy to read from that, but anyway, that's the game. So I can do, let's see, let me examine the stack. Up here in the stack, right? We've already seen all that. Okay, that's what I wanted to show you. So now we're going to examine an overflow with this long input again. So I run, and yes, start from the beginning. Now I put in that long string, and now I examine the stack again. And here is the original return pointer. Here's the data I put in. Here's what I've replaced it with, 24, 28, 28, 2C, 2C. And so if I continue, I end up there, 24, then 28, then 2C. So I just verifying that right there is where I control it. So now I know how to do it. So now we can make an exploit. So I can get out of here. And I want to get out of here, quit, yes. All right, now let's just take a look at the first exploit. All right, so here's that same string. And then I broke it off after the first 3 24s because the next 8 bytes go into the instruction pointer. So first I put in A0, B0, B0, C0, C0, D0, D0, just so I can tell if I'm able to hit it accurately. And then I... After that, I added an op sled and a break. And I just found some, there's no instruction called NOP in the ARM processor, but I found one that does nothing. I think it copies register 1 to register 1. There are instructions like that that actually do nothing. So that's one of these. And here's something that causes it to break and go back to the debugger by being a forbidden instruction. Again, it's not exactly a break instruction, so I found equivalents, and I put at the end of the project how I found them. Anyway, so now I have an attack prefix plus the program counter plus NOP sled and buffer. So if it works, then I can jump into the NOP sled, execute this, and hit the break at the end, which will show that I'm able to inject code and execute it. That's the point here. So this is EX1. And I ran it and put it in a file called ATT1. And so as you can see, it's pretty long. If I do XXD on ATT1 to see what's in there, I got to install it. All right. All right. And so here you can see, here's the 110.14.14.1c. Then comes this A, B, C, D stuff I'm putting in the instruction pointer. Then come a whole bunch of repeated instructions. This is the NOP sled, the stuff starting with 1F200. And this is the brakes down here. So that's what I've injected. And this is going to be the shellcode. So yeah, I can now get back into the debugger. All right, GDB minus Q PWD. And now run, taking the input from ATT1. All right, and it stops with A, B, C, D in the instruction pointer, which is what I wanted. And so now I want to examine the stack. I'll do x/ADX at the stack pointer. And so here I have my NOP command, and here I have my brake command. So the point is, I just need the address I want to jump to is any address up here. Any address in the middle of my NOP sled will do. I always put it in the middle and make a big NOP sled so I can afford to have errors because programs often are a little bit different in real memory when running than they are in the debugger. So it's good practice to give yourself a NOP sled. So I pick some address in the middle, like F360. And that'll be ex2.py. And so here we are. I chose F380 last time. That'll work too. F380 is in the NOP sled. Doesn't really matter which one. And so I just put that in as the address all backwards. 80, F3, and then a lot of Fs, then some zeros. And I got NOP sled in the buffer. So this one should actually run the NOP sled and my fake shellcode. NOP sled followed by just effectively a break command. So I go back into GDB, and I run taking the input from ATT2. And all right. And so you'll see it hit this illegal instruction, which is my break, and it hit it at 3D8, F3D8. And if you go back up here, that is just what I expected. Here it's doing my NOP, 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 and 3D8 is when it hits this command. So it works. It executed some of these NOPs and made it to the first break. So that proves I'm in control of the box. I can inject code and I can run the code I injected. So now all you have to do is make some exploit code. And it turns out that Metasploit does have some payloads for ARM64. You install Metasploit. You can search for that. Let's get out of here. This will go to MSF Venom and list payloads, and I'm going to look for 64-bit ARM architecture and Linux. It turns out there's quite a few. And the simplest one is the last one in this list that will just make a reverse TCP shell. So it will let you have a command line like a terminal over the internet. And so you can see the options for that one. You choose that option, choose that payload, and then list the options for it. And it'll show you the only option you have to set is the listening address, of course. One box can exploit another box. So I can now generate my shellcode. I just need the IP address. And there's the IP address of this device. And I'm going to generate this. And the command to generate the shellcode is this, which is going to make that attack for 64-bit ARM with the local host set there and format Python. And I just have to paste in the right address, which is this 172 stuff. So I copy that. I go down here and replace the address with the right address. All right. Oops. There we go. And that should do it. That should create Python code, 762 bytes. All right. And that's what I've already inserted into my ex3.py here. So you see it's very much the same. You got the same prefix. You got the same address here to hit your NOP. You got the same NOP sled, but then your buffer is now that code they provided. And you just put that in instead. And the one thing that might not be obvious is the Metasploit makes modern Python 3 shellcode, which is a byte string. But in this case, I have to turn it into hex because of the way it's working. So that's the only thing you have to do. And so I've put that in ATT3. And so now my exploit should work. So I need a second shell to test it in. And I've got one here. you have to make a listener to pick it up. And so MSF console is Metasploit again, the other part of Metasploit. And here you specify the exploit and the payload. Let me just put this, okay. So you specify the exploit, which is multi-handler, and then you tell it what payload you're using. And then I set localhost to 0000 and local port to 4444, which is the default. So it will listen on all interfaces for traffic coming in on port 4444, and then run. So now this is my command and control server running to take over the box. And let me just make these both fit on the screen at the same time. There we go. All right, and so here I just have to run the program, pwd, okay. Okay, and take the input from ATT3, and when I do that, it says it's all done, and up here, there we are, the command session shell is opened. So now I have control of that box, I can do ID and so on. I can now execute commands up here, and there's a particular command you do to find the flag. So that's what I wanted to show you. That's a complete exploit where you take over the box. All right, that's what I wanted to show you. I'm going to stop this recording.